Hi everyone. In this video, we will discuss the independence of path of line integrals of certain vector fields. In a previous video, we saw that the line integral of a vector field f is independent of the parameterization of the path that we choose. However, we noted in earlier videos that line integrals are not always independent of path, which raised the question of what class of vector fields do have line integrals that are independent of path. So today we will investigate that question. We'll prove necessary and sufficient conditions for the independence of path. And we will also, along the way, develop a couple of fundamental theorems for line integrals. So to begin, I want us to be clear about what we mean when we say that the line integral of a vector field is independent of path. So imagine that we have a vector field f that's defined on some open connected set S. We say that the line integral of f is independent of the path in S if for every pair of points in the set S, the line integral has the same value for all piecewise smooth paths in S joining A and B. So the idea here is okay, you have some set S, right? And we will say that F is independent of path in S if for any 2 points in S, so imagine I have 2 points A and B, okay? If I take any path between these 2 points, all right, there's one path, maybe alpha 1, maybe here's another path, alpha 2, right? And notice we only require that these be piecewise smooth. So maybe alpha 1 looks like it's probably smooth. Alpha 2 maybe is piecewise smooth. But regardless of which path I take here, maybe this is some other path, alpha 3, as long as this path stays in S, then we would say that f is independent of the path in S if this integral of f d alpha k, right, is equal to the integral of f d alpha j for all k and j, right? So essentially, if you have any path alpha I connecting A to B, then for all of those paths, you ought to get the same value of the line integral. So the actual value of the line integral is completely independent of the particular path that we take between those 2 points. Now, again, we saw in a previous video that this is certainly not always the case. So our goal today is going to be to prove a theorem that will tell us when we should expect that line integrals will be independent of path. Okay. So I've put a statement of the theorem out. The overarching goal of this video is going to be to prove this theorem. So we're going to talk through this theorem. You can see I've got a couple of terms in different colors here. We're going to need to define those terms. And then we're going to need to slowly work through this theorem. So let's just read the theorem through first. So let F be a vector field, which is continuous on an open connected set S in Rn. The word connected actually popped up earlier, but it's not actually a term we've formally defined. So let's take some care in a minute to define that. Then the following 3 statements are equivalent. Okay. So before we get to those 3 statements, when we say these 3 statements are equivalent, we mean each statement if and only if each of the other statements, right? So if I just think of these as statement 1, 2, and 3, 1 holds if and only if 2, if and only if 3. So, right, either all 3 of these are true or all 3 of these are false, right? They're all equivalent ways of saying or expressing the same thing. So the first is that f is the gradient of some potential function in S. Now, we need to define here, so this is not a potential function is a particular type of function. So this isn't potential in the like normal English language sense. But this is really just saying f is the gradient of some kind of function in S. The integral of f is independent of the path in S. So if we just immediately look at these two are equivalent. right? And this is saying that the functions whose line integrals are independent of path in S are precisely the ones, the vector fields that are the gradient of some other function. Okay, so if your vector field f is the gradient of some function, then you should expect that your line integral of that vector field will be independent of the path. Now, the third piece of this is that the line integral of f is 0 around every piecewise smooth closed path in S. Okay, so again, all of these are equivalent, right? So saying that f is independent of path in S means that the line integral of f is going to be 0 around every piecewise smooth closed path in S, right? So again, all of these things are connected to one another. But we want to first, before we delve into like how are we going to prove this, let's first take a couple of minutes to just talk about a couple of these terms. So the first term I want to talk about is connected. So connected is actually a topological notion. And actually the definition we have up here is what you would in a topology class probably call path connected. The topological definition of connectedness is a little bit different. For our setting, since we're just working in Rn with the normal metric topology, these are equivalent, and so it's okay. But so we'll use this definition of connected. I just want you to understand that if you go take a topology course, this will not be the definition of connected. But we say that an open set S in Rn is connected if every pair of points in S can be joined by a piecewise smooth path lying entirely in S. Okay, so that's sort of an example, right? I mean, if you just think of a normal sort of blob in Rn, right, this is connected because if I take any 2 points, right, I can always connect them with some path, right? Now, you can already see sort of, we just need this out of necessity for a line integral to even be defined, right? I would worry if I had a set S, so what would a non-connected set look like? Well, just imagine, say, this is your set S, the union of these 2 blobs, but these 2 blobs are disjoint, right? I could take 2 points in S, right? Both of these are in S, but I cannot connect these with a path that lies entirely in S, right? Because I would have to go outside of S to connect them. This really is just out of necessity, right? We're assuming we have all these things that are defined on S. And if I want my line integral to be defined on S, then I need to make sure there's some path between these 2 points that stays in S, right? If there's no path between these 2 points that stays in S, things sort of, they might either become sort of vacuously true or they generate weird counterexamples. We don't want that. We want any 2 points to be able to be connected by at least one path, right? And since we're talking about independence of paths, right, we really like it to be many paths, but at least one path. You may see in some places, other books, not so much our book, but other places may call this a region or a domain. They may give sort of a specific term to open connected set. At least for the purposes of this video, any set S we're talking about is going to be some open connected set. But this connected piece is important here. All right. The other definition was a potential function. Okay. Now, in a way, if we go back to that definition, we could just replace potential function with function. Okay. Something is called a potential function for a vector field f if its gradient gives you f. So here we have psi is called a potential function for f because the gradient of psi is equal to f at every point of S. Okay, so we really are thinking about, right, this theorem is saying to us, well, we should expect that our vector field f is independent of path if and only if it is the gradient of some scalar function psi. So here, gradient of psi is equal to f. Okay. There's sort of a lot of terminology around this too, or just other terminology. So if f has a potential function, then we say that f is a gradient, or we may also say that f is a conservative vector field. And in fact, we will come back. It turns out that conservative vector fields generally have nice properties. So we will study those a little more as we continue throughout the course. But again, really all we're saying here is f is the gradient of some potential function. That really just means f is the gradient of some function. The function that happens to be a gradient of is called the potential function for f, or I should say a potential function. As you might imagine, these can be equivalent up to scalars. So it's just important to be a little careful there. All right. So here's our theorem again. Let's think about a plan here, right? So if I want to show these things are equivalent, right, really that means, all right, statement one, if and only if, statement two, if and only if, statement three, if and only if, statement one, right? All of these should be if and only if the others, okay? But to prove this, I don't really want to prove one if and only if two, two and if and only if three, three if and only if one. And as we've seen before, right, typically when we want to prove these sort of the following are equivalent things, one strategy might be to show one implies two, two implies three, and three implies one, right? So in this case, we'll first prove one implies three. We will then prove that two implies one. And then finally, to complete the proof, we will show that 3 implies 2. Okay. Oops, I should circle that whole thing. Yeah. And so you'll notice we will have shown 1 implies 3, 3 implies 2, and 2 implies 1. So if you wanted to show that 2 implies 3, well, 2 implies 1 and 1 implies 3, therefore 2 implies 3, right? So you're able to get all of the possible implications, right, just by proving this cycle. So the first thing we want to focus on proving is that 1 implies 3. So we want to show that if f is the gradient of some function in S, then the line integral of f is 0 around every piecewise smooth closed path. Now, in order to do that, I am going to need to build some machinery. In fact, for the first two parts of this proof, I'm going to need to build some machinery. And so we will first build that machinery it's going to be a theorem that we need to prove. Then we'll see how that fits into our plan. Then we'll build the other piece of machinery, see how that fits into our plan. And then finally, we'll come back and tie it all together. All right, so the first piece of machinery we're going to need is going to be the second fundamental theorem for line integrals. So let psi be a differentiable scalar field with a continuous gradient, which we'll just call gradient of psi, on an open connected set S in Rn. Then for any 2 points A and B joined by a piecewise smooth path alpha in S, we have that the line integral from A to B of the gradient of f d alpha is equal to, gradient of psi d alpha is equal to psi of B minus psi of A. Now, again, you'll note here that this looks fairly similar to the second fundamental theorem of calculus, right, which would have said that the integral from A to B of f prime of t dt is equal to f of B minus, should be lowercase, minus f of A. Okay. Of course, the difference here, right, is that we're dealing with a scalar field, and the differential operator here we're dealing with is the gradient, right? But still, this idea that I should be able to evaluate the integral of of this differential thing by just evaluating it at the endpoints, right? Which is exactly what we have here. All right. Now, not shockingly, we are actually going to make use of the second fundamental theorem of calculus in our proof of the second fundamental theorem for line integrals. So let's see then how this works. Okay. So here is our proof. Okay. So again, our setup, we have 2 points A and B in S. We're going to join them by some piecewise smooth path alpha. Now, to begin with, I could deal with the piecewise smooth case. Let me actually just start with alpha being smooth. Then we'll see how to fix things if it's piecewise smooth. So, and let alpha be a smooth path connecting, a smooth path defined on AB so defined on the interval AB with alpha of alpha of scalar A equal to vector A, and alpha of scalar B equal to vector B. So the idea is this is some path that maps the real interval AB to some path that starts at vector alpha and ends at that starts at vector A and ends at vector B. Okay, so this is just sort of the setup. And we're going to assume, again, for the time being, not that it's piecewise smooth, but let's actually assume even more. Let's assume it's just totally smooth. Okay. Then if I look at the integral of the gradient of psi d alpha, well, by definition, that's going to be the integral from A to B of the gradient of psi evaluated at alpha of t dotted with alpha prime of t dt. Okay. So again, this is just the definition of the line integral. Okay. And so if we note that if we define g of t, okay, I'm going to define this sort of auxiliary function to work with, which I'm going to call g of t, and g of t is going to be defined as psi of alpha of t. Then the derivative, okay, g is a scalar function, right? It takes as an input a real number. And over here, what do we spit out? Well, you put a real number into alpha, that gives you back a vector. But psi is a scalar field, so psi of this vector alpha of t gives you back a scalar. So I'm inputting a scalar t and I'm getting output a scalar. Okay, so this is a real valued function of a single variable. I can take its derivative. To take its derivative here via the chain rule, I need to take a derivative of this. So this is the gradient of psi evaluated at alpha of t dotted with alpha prime of t. Well, notice that's actually just precisely our integrand up here. So then we can express this integral of the gradient of psi, the line integral of the gradient of psi. We can express it as the integral from A to B of this thing, which is just g prime of t. Now, notice that we actually should have taken a little care up here. Like, how do we know all of these things are differentiable? Well, if we go back to our conditions, right, we are assuming that for the second fundamental theorem of line integrals, right, we're assuming that all of these things are differentiable. This is smooth, so this exists and is continuous, right? This is continuous. So this is continuous. So we have a derivative down here, which is continuous, and therefore integrable, and we can apply the fundamental theorem of calculus, right? Again, this is now just a scalar function. So this should really just be g of b minus g of a. Okay. So here I'm just applying the regular second fundamental theorem of calculus. Okay. But now let's see, what is g of b? Well, g of b would be psi of alpha of b minus g of a would be psi of alpha of a. But alpha of b is just vector b, and alpha of a is just vector a. So this is psi of b minus psi of a. And so notice, even though I haven't written it over here, right, alpha is a path that connects the vector a to the vector b. We might sometimes even re-express that explicitly here, right? And so I have that the integral of the gradient of psi d alpha from a to b, right? Alpha is a path connecting a to b, is equal to psi of b minus psi of a. Okay. Now that actually proves the second fundamental theorem of line integrals if my path alpha is smooth. But what if it's piecewise smooth? Okay. Well, let's break that out as a quick separate case. If alpha is piecewise smooth, then we'll just pick a partition xi of the interval AB such that alpha is smooth on each subinterval of the partition. Xi minus 1 to xi, say. Okay. So if it's piecewise smooth, that means you can break it into a finite number of pieces such that it is such that it is smooth on each of those pieces. So you can pick this partition that will do that. Let's say, just for to be helpful in a minute, the partition contains n things. Okay. Well, then, if I want to calculate the integral from a to b of the gradient of psi, line integral of the gradient of psi d alpha, then I can just break this up, okay, and I can do the integral on each piece. So the sum I equals, and sorry, this should actually, right, partitions are indexed starting at 0, x0 is equal to a, xn is equal to b. So this would be the sum 0. Nope, sorry, here on this sum, sorry. So these are indexed with respect to 0. On the sum, I'm going to index starting with 1, and this will be the integral from alpha of x sub I minus 1 up to alpha of xi. So I'm breaking up each of these so that we're doing it on the subintervals where it's continuous of the gradient of psi, line integral of the gradient of psi d alpha. Okay, so I'm just breaking this up so my integral is over each of these continuous pieces. Now, in each of these pieces, my alpha is smooth. Okay, so now in each of these pieces, I can apply this result. So on this piece, I'll get psi of alpha of xi minus psi of alpha of xi minus 1. Okay. But now if I look at this sum will actually be telescoping. And so what I'll end up with is psi of alpha of xn minus a psi of alpha of x0. But xn is just b, and alpha of b is vector b. And x0 is just a, and alpha of a is vector a. And so you see that even when it's piecewise smooth, I still get the same result. I just have to go through applying this piece by piece on smooth subintervals. So this fully proves the second fundamental theorem for line integrals. Now, we want to see, it's not immediately clear maybe, right? I mean, this seems like a nice, interesting theorem, but what does it do for us in terms of proving our main result that we wanted to prove today? Well, let's go back to that, so we can get the board erased here. Let's go back to that and look at that theorem again and see how this will help us. All right. So toggling back here to our main result, okay, right, our goal was that this would help prove that 1 implies 3. So how could I use this to prove that, say, 1 implies 3? Okay. Well, if f is the gradient of some potential function in S, then what would that mean? That means f is equal to the gradient of psi for some psi. That's what it means to for f to be the gradient of some potential function. Okay. Well, okay, if that's the case, then what if I looked at the line integral of f? Now, around some closed path, well, that really means that it starts and ends at the same point, right? Right, a closed path starts and ends at the same point. So this is like an integral, a line integral from a to a of f, but f is a gradient. And, well, I ought to be able to use the second fundamental theorem of line integrals on this, so this ought to be psi of a minus psi of a, which, well, that's just something minus itself, is clearly 0. Okay, so 1 implies 3 follows fairly immediately from the second fundamental theorem of line integrals. Okay. All right, now our next goal is going to be to prove that 2 implies 1. Now, on the surface, I think this one seems to me, at least at the outset, much more difficult. And one of the reasons it seems more difficult is I understand how to use, as my hypothesis, f is the gradient of some potential function. That means I can just start by saying, okay, let f be gradient of psi for some function psi. It's unclear to me how to use the line integral of f is independent of the path s. But this is actually, it turns out to be sort of an interesting result. And I think the way that this is used is sort of something we don't see in a lot of other places, although it's a really important way to use a hypothesis. Okay. So I mentioned, we're going to prove these by building some machinery. So we proved that 1 implies 3 by building the second fundamental theorem of line integrals. We're now going to prove that 2 implies 1 by building the theorem, which is the first fundamental theorem of line integrals. So let's look at that theorem. So this says, let f be a vector field that's continuous on an open connected set S, and assume that the line integral of f is independent of the path in S. Then let a be a fixed point of S. So I'm just thinking like a is some fixed value, and I'm going to define a scalar field psi on S by defining psi of x to be the line integral from a to x of f dot d alpha. Now, notice that, then the conclusion is if we define psi in this way, then the gradient of psi exists. And not only that, the gradient of psi is just F. Okay, it's just the vector field F. Now, the first thing to note is that this is really analogous to the first fundamental theorem of calculus, right? First fundamental theorem of calculus usually says define a function capital F to be the integral from a to x of f of t dt. Then capital F prime of x will just be f of x. Okay, so this is the first fundamental theorem of calculus. You can see over here, what are we doing? We're defining a function as some sort of integral. And then we're saying if you take the appropriate derivative of that function, it's just the thing you were integrating. Okay, so this is very much analogous to the first fundamental theorem for the first fundamental theorem of calculus. And again, maybe not shocking, we're going to use the first fundamental theorem of calculus to help us prove this. Now, you'll notice again here in the statement of this theorem, one hypothesis is that this only works if the line integral of f is independent of path. And you might wonder, well, where does that come into play? Well, notice that if f is not, I haven't said anything about a path alpha, right? And the reason I haven't said anything about a path alpha is it doesn't matter what path I pick here, this function will be defined and will have one specific value for any path alpha I pick because the line integral of f is independent of path. Okay, so here, the fact that the line integral is independent of path plays the role of providing us that this function is even well-defined, right? This function would not be well-defined if the line integral of f was not independent of path, because then you would say, well, I don't know what path to use, right? And maybe you could then say, okay, well, pick a particular path, but this x is changing all the time. So that would be quite problematic. You know, you might be able to do something that says, well, okay, choose the linear path, but then you have to change your conditions on your set S because you're guaranteed that there's some path in S between A and X, but not that there's a linear path. So then you have to assume. So anyway, it plays this really nice role of just providing us in an easy way with the fact that this function is well defined. Okay? So even though we might not sort of formally otherwise stated, that's really the role that this independence of path hypothesis is playing in this theorem. All right, so let's prove this. Now this result, there's a little more sort of setup here, but the payoff at the end is pretty slick. Okay, so what we're going to do is we're going to choose a value h, or well, we're just going to let h be sufficiently small so that the difference quotient I want to look at is going to be psi of x plus hy minus psi of x over h is well defined. Okay. So the book actually spells this out in a little more detail. The idea is, as long as h is small, since x is in S and S is open, for a small enough h, I should be able to guarantee that for every y, this thing is defined. Okay, that's essentially the idea. I don't want to get bogged down in the exact details of, you have to select a ball of some radius around x, and then do it. Like, we just need to select h sufficiently small so that this will be well defined. Okay. And now what we want to do is, if we look at this difference quotient, right, this sort of looks like, or it's actually exactly the difference quotient we would use if we wanted to define the derivative of psi at x with respect to the vector y. Okay. Now, if you think about here, our goal is to show that this function psi, which we have defined, is, we need to show that its gradient is equal to f. So I don't actually need the derivative with respect to any arbitrary vector. Eventually, I'm going to need it with respect to ek, right? For each k, right? I need to show that the partial derivatives are equal to the components of f. That's what I need to show. But let me start with this sort of arbitrary form. Okay. All right. So by additivity of the line integral, okay, if I look at this numerator, so psi of x plus hy minus psi of x, okay. So this is going to be, right, that function psi was defined as the line integral from a to, in this case, x plus hy of f dotted with d alpha, so minus the integral from a to x of f d alpha. And so now using the additivity, so this is just definitionally what each of these pieces means. Now using the additivity, so integral from a to x plus hy minus integral from a to x, this is going to end up just being the integral from from x to x plus hy of f d alpha. And the path joining x, right, to x plus hy could be any path, right? As long as it lies in S. Okay. In particular, I want to choose a particular path. Okay. So if I take alpha of t to be x plus thy for t in 0, 1. Okay, so notice that when t is 0, right, that just gives me x. When t is 1, this gives me x plus hy. So this path is going from x to x plus hy. Now, again, you might be concerned, how do I know this path lies in S? Well, this goes back to choosing h in the right way. So if I choose h sufficiently small so that this difference quotient is defined for every y, that means that this path will necessarily, the fact that x plus hy is in the domain, is in S for every y, means that this path will be in S. So if I define alpha t in this way, then if I take this whole thing now and divide it by h, so I've got psi of x plus hy minus psi of x, and I divide by h. Okay, that would be 1 over h times this integral. Okay. But now I have a particular alpha, and so I should plug in what that is. So this is 1 over h times the integral from x to x plus hy. Oh, sorry. I'm converting this now by the definition to the Riemann integral. So this is going to be from 0 to 1 of f of alpha of t, so f of x plus thy, dotted with alpha prime of t. Well, here, having defined alpha in this way, alpha prime of t is just going to be hy. Okay, so this is going to be dotted with hy dt. Okay. Well, h is a scalar, so it can be pulled out of this dot product, and it's independent of the variable of integration. It can actually be pulled out here. So h times 1 over h is just going to give me 1 for all h not equal to 0. And so this will be f of x plus thy dotted with y dt. All right. So all I'm doing here is I'm exploring this difference quotient, right? Eventually this is going to help me say something about a derivative. I'm just doing some expressing of that in terms of this particular Riemann integral in this case. All right. Now, I want to keep in mind the fact, like I said before, this right now, this looks like the difference quotient for the derivative of phi at x with respect to an arbitrary vector y. I really want to look at the partial derivatives. Okay, so let's do that. Let's take y to be, let's look at an arbitrary coordinate vector, right? So let's look at ek, right? So that's the vector that's all zeros, except for in the kth position where it has 1. And so then if we look at this difference quotient now, I have psi of x plus hek minus psi of x over h is equal to, now I have the integral from 0 to 1 of f of x plus thek dotted with ek dt. Well, if I look at this, if I take the inner product of any vector, I mean, this is a vector field, so it's a vector valued function. But if I take the inner product of any vector with ek, all that's going to do is pull out the kth component. So what this is going to do is actually give me the integral from 0 to 1 of the kth component of the vector field evaluated at x plus thek dt. Okay. And the nice thing to note here is that this thing right here is this is a scalar function, right? This is just a scalar valued function of several variables, right? Or of a vector. You plug in a vector, but you get out a scalar. Okay. Now, I'm actually going to do one more thing here. Okay. I'm going to do a u substitution. I'm going to let u be equal to th. So then du will be equal to h dt. And if I do that u substitution, this is going to become the integral from 0 to h of f sub k of x plus u ek. Now my dt is going to be replaced by 1 over h du. I'm actually going to bring that 1 over h out front. The dt. All right. Now you might be looking at this and going, I'm not quite sure where we're going, how this is going to help. Okay. Well, in just a second, the first fundamental theorem of calculus is going to come to save the day. Okay. So we're going to define g of t. So let g of t be equal to f sub k of, or sorry, let f g of t be equal to the integral from 0 to t of f sub k of x plus u e k du. And sorry, over here, this should be an integral du, right? I did that change of variables. Be du. Now, if I do this, then I can actually, if I look at this, this is just G, this is G of H. This term is just G of H. This is 1 over H. And G of 0, if I plug in that, I'll just get 0. Okay. So what I have then is that this quantity, okay, psi of x plus h ek minus psi of x all over h. I actually get that this is equal to this, which is the same as g of h minus g of 0 all over h. Okay, now, again, you might be looking and going, I'm still not quite sure where this is going, but notice that both of these, I'm going to do some erasing, but I'm not going to erase this stuff in green. Notice that both of these things now look like difference quotients, but they look like difference quotients for different objects, right? The thing on the left-hand side looks like a difference quotient for the partial derivative of psi with respect to the kth variable. Okay. The thing on the left-hand side is something about it's a difference quotient for a partial derivative. The thing on the right-hand side is a difference quotient for a scalar valued function. Okay. And somehow, actually, that scalar valued function depends, the scalar valued function g, it actually depends on the kth component of f. Okay. So I'm starting to get something about, derivatives of psi in terms of f. So let's see with this how we actually finish. So let's then just, if I take a limit of both sides, well, the limit as h goes to 0 of this just gives me the derivative with respect to the kth variable of psi evaluated at x. So this, by definition, is the limit as h goes to 0 of psi of x plus h ek minus psi of x all over h. Okay. But now we've already discovered that this quantity is equal to this quantity. So this ought to be the same as the limit as h goes to 0 of g of h minus g of 0 over h. Well, this is a scalar function. This is just, oops, I'm sorry, I've written up a bit into the, so this is g of h minus g of 0 all over h, okay? So this is now just a difference quotient for g, and g, it's actually a differentiable function by the first fundamental theorem of calculus. So by the first fundamental theorem of calculus, g is differentiable. So this limit exists. It will be g prime of 0. So this is actually equal to g prime of 0. The question is then, what's g prime of 0? Well, the first fundamental theorem of calculus says the derivative of this, g prime of t, ought to be equal to what you get when you just plug t into the integrand here, okay? But I'm plugging in 0 for t. So I'm actually just going to get f sub k of x plus 0 ek. Well, notice what we have here. I now have that the derivative with respect to the kth variable of psi is equal to the kth component of the vector field f. So hence, I have that this holds, but for every k, right? K was arbitrary. So this holds for all k between 1 and n. And so the gradient of psi, right? This is a vector, but its components are each of these things. Right? So what you're showing here is that each of the components in these vectors is equal. Well, if each of the components are equal, then the vectors themselves are equal, okay? Which is what you want to conclude. Right? So again, We get a version of a first fundamental theorem of calculus here for line integrals. And nicely enough, you actually use the first fundamental theorem of calculus in proving it. Okay. Well, now we've established that, of course, it raises a natural question. How does this help us? This was not our goal. This was simply a tool along the way. So let's go back to our main theorem to see how this can help. All right, so we had already showed that 1 implied 3. We were now trying to show that 2 implies 1. So if I want to prove that 2 implies 1, okay, I'm going to assume that the line integral of f is independent of the path in S. Once I know that, I can use the first fundamental theorem of line integrals, and I can just define psi to be the integral from a to x of f d alpha. The first fundamental theorem says that then the gradient of psi has to be equal to f, which means I've found a potential function, right? This function psi, the first fundamental theorem of line integrals tells me if I define my function psi in this way, then the gradient of psi will be f. So this function you end up with is in fact a potential function for f. Okay, so 2 does in fact imply 1. All right, now I mentioned to finish the proof, okay, we need to do one more thing, okay? And in fact, this is probably the easiest piece of all. It's actually easy enough that I'm going to sort of just sketch it out. You could write out the details if you want, okay? So to complete the proof, right? So where are we at? We first showed that 1 implies 3. We've now shown that 2 implies 1, so I better show that 3 implies 2. Okay, so what's the plan there then to complete the proof? So if I want to show that 3 implies 2, just to back up here for a second, I get to assume that the line integral of f is 0 around every closed path. I need to use that to show that the line integral of f is independent of path. Okay, well, the sketch of the proof. So here's sketch of 3 implies 2. So the idea is take 2 points in S. Okay, and I'm using sketch very literally here because I'm going to draw a picture. Okay. And so here's S. Take 2 points, 2 arbitrary points A and B in S. Okay. And connect them via 2 different paths. Okay. So imagine this path in red is alpha 1, and this path in orange is alpha 2. Okay. Now, what I'm going to do is I'm going to define a closed curve, gamma, which is going to start and end at A. And what it's going to do is it's going to follow alpha 1 all the way to B. And then once it gets there, it's going to come back and it's going to follow alpha 2, but in the opposite direction back to A. Okay. I'm going to call that gamma. Okay. Well, gamma is now a closed curve, right? And I haven't drawn these as overlapping, right? But gamma really, it would be right on top of alpha 1 and then right on top of alpha 2, but coming back in the other direction. Okay. Well, the idea is then you look at, you know that the line integral of f d gamma, right, that has to be 0 because gamma is closed. And that's what you're assuming. You're assuming that the line integral along every closed path is 0. So this is 0, but at the same time, let's see, I can break it up into sort of an integral from here to here plus an integral from here to here, right? So I can think of this as an integral from A to B of f d alpha 1 And now when I come back here, right, this integral from b to a, it's going in the opposite direction of alpha 2. So it's really negative the integral from a to b of f dot alpha 2. But now notice I have that this difference is equal to 0, which just implies that the integral from a to b of f along alpha 1 is equal to the integral from a to b of f along alpha 2. Okay. So what this proof really shows is that anytime you have an integral along two different paths going from a to b, those have to be equal to each other, because you could pair them up in a certain way to make a closed loop that would give you a zero line integral. Okay. So that is the sketch of the final part, which completes our proof. So that mostly completes our video. I do want to go back and take one last look at the theorem, and which will help motivate where we want to go in our last video talking about line integrals. So what I see now when I look at this theorem is I really see that two really nice things happen when my vector field is the gradient of some potential function. Okay. So the immediate question that raises is, well, how do I know if I'm looking at some vector field, how do I know if it's the gradient of a potential function? Okay. Well, it turns out that that is not necessarily super easy to do. It requires a little bit of work. But what we will look at next time are both some ways we might go about determining it directly and actually calculating the gradient function, but also looking at some sufficient conditions that might just serve as quick checks to help us see, in some cases, when f is the gradient of a potential function. So we will conclude our discussion of line integrals by helping to answer the question, when is f a conservative vector field, or when is it the gradient of some potential function?